we have an input f of s. So, and we're thinking about this in our s-plane or our complex space. That's what the s variable is for. Into our system, h of s, and we have an output x of s. Right? So we've talked about this before. This is all kind of, you know, our general systems modeling diagram for any vibrating system, right? So we wanted to find a transfer function h of s, but now we want to find h of s, right? So our question here is, what is h of s? We haven't talked about that at all, right? And so we want a transfer function that relates our input to our output. So we want one mathematical equation, so I can put whatever I want as my input, and I'll get my appropriate output, right? So you can see how that transfer function of a system would be very important. So let's show the reasoning behind a transfer function here. Behind h of s. So here we will show that the output of any system can be related to the input through a series of polynomial coefficients, right? A and B. So our output is related to input through ROUGH, a series of polynomial coefficients. Right, so if you think back to calculus, think of like a Taylor series expansion, right? What's powerful about a Taylor series expansion is you can build almost any time series signal that you want, right? You have to have enough terms, and those numbers of terms may get, you know, impractical, but theoretically you can get to pretty much any time series you want, right? I don't know what the proof is if it actually allows you to get any time series, but you can get very complicated things. So we're going to do that same thing here, but just consider a general nth order linear time invariant differential equation, right? So let's go ahead and draw out what a polynomial expansion would look like. So we have a to the n, right? We just have some scalar term of dx, or sorry, d to the n x of t over d of t to the n plus a to the n minus 1 of d to the n minus 1 x of t over dt to the n minus 1 plus whatever else we want, you know, depending on how many n's we have, plus a naught x of t, right? So this is our output, right? That at least should make sense, and you can think about that as anything you want, right? It's not one specific sinusoid or a collection of sinusoids, but it could really kind of be anything. Yeah. So we can relate that to our input, right? We can set that equal to a certain number of coefficients to our input. Let's call that b to the m. And so these don't have to be the same number of coefficients, right? B to the m times d to the m of f of t over dt to the m plus b to the n minus 1 dm minus 1 f of t over dt m minus 1 plus whatever you want plus b naught f of t. Right? So you can go ahead and describe about anything you want using these two terms. Right? Just generically kind of thinking about this from a 5,000 foot view in your crappy little Cessna 210. If you're looking down on your transfer problem from that space, just think about it like this, right? So where x of t is the output, right, and f of t is our input. So we can go ahead and take the Laplace transform of both sides of this equation, right? So if we take the Laplace transform of the left side, actually, I'm just going to go ahead and move my charger. Maybe I can do that. I'm just going to go ahead and write these in green. So let's take the Laplace transform of both sides, right? So that all of a sudden gets a whole lot easier to write. It's just going to be a to the n. It's constant, right? So it's going to go through the Laplace. A to the n times s to the n, depending on how many derivatives we take, times x of s plus a to the n minus 1, again, it's constant, it's going to go right through, times x of s, or times s, n to the minus 1, x of s, plus however many other terms we have, a naught x of s. Right? But now we also are going to need our initial conditions. For x of t, right? So we need our initial conditions. And on the right-hand side, we can do the same thing. But let's go ahead and call that, let's still keep with our equals in purple, pink. On the right-hand side, we are going to have b to the m, sm, fs, plus b to the m minus 1, s to the m minus 1, fs, plus dot dot dot, plus b naught fs, plus initial conditions. But this is our forcing, so it's for f of t. Oh, yeah, for f of t. Hey, so however, often let's, a couple classes have we been worried about our initial conditions, right? So that how many times can I say that? So the initial conditions are going to give us our transient or our steady state response. What do we care about? Yeah, so that's a good question. Do we care about the steady state? No, let's say not, because it's easier. Sorry, we care about the steady state, yes. We don't care about the transient. Let's just worry about the steady state, because it's an easier thing to understand, right? Transients are always hard. Does that make sense? So if we drop our initial conditions, we drop all understanding of the transients in the system, which are important, but not what we're considering right now. Let's tackle one thing at a time and just do the steady state. That work? So let's go ahead and consider the steady state. So considering just steady state, what we get now is a to the n, s to the n. I'm going to pull out all of my xs's, plus a to the n minus 1, s to the n minus 1, plus a naught. Multiply that all by definitely not x to the subscript, xs, is equal to bm s to the m plus b m minus 1 s m minus 1 plus dot 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 plus b naught fs. Right? So we could go ahead and rearrange equation 52 to solve for a relationship between the Laplace variables x and f. Sorry, x and f. So by algebraic expression, right, we get x of s over f of s is equal to I really shouldn't do that. It's going to be on bottom, isn't it? Let me write it out, because when I copy to save time, it just makes people who are taking notes by hand fall behind. Bm Sm plus Bm minus 1 Sm minus 1 plus dot 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 plus B naught f of s. Right? I don't need that. You are correct. Thank you. Okay, so now we have an algebraic expression on our right-hand side, and we can just go ahead and that is going to be our transfer function, right? So this shows that the ratio of the, I'll just write it, is equal to h of s, right? This shows that the ratio of the input algebraic expression to the output algebraic expression is equal to the ratio of the Laplace variable of the input Laplace over the output, right? So we define, h of s as equal to x of s over f of s, right? And it's not a pure ratio, right? Because you can have multiple degrees of freedom, and this is how you get how your input is expressed in terms of how your input is expressed in terms of your output is your transfer function, transform function. That makes sense? Okay. So h of s is going to encode all of the information that we have about our system. So what's powerful here is if you have a transfer function and you're only concerned about the steady state in your transfer function, right? You can put whatever you want into it and you'll get your output, right? So now you have one equation that you just throw any number you want, any series of numbers you want, and you'll figure out how that system is going to respond.
Review 4.4, frequency and time domain. Up until this point, we've only talked about things in the time domain, which you can kind of get from this perspective, right? I have a signal here in red, and I am moving up and down and rotating that signal around. And maybe this is, maybe that's described as like a x of t, right? So that gives me my time domain. We all live in the time domain. Fourier taught us, and there's a wonderful 3 blue, 1 brown video on YouTube about the Fourier transform. I would highly recommend you go take a look. That number of systems, thermal, frequency, structural dynamics can also be explained in a frequency domain. So what is a frequency domain, right? So here on a frequency domain, I might have a spectrum of omega is how we're going to write that in this class. And I can take a summation of my time signals and I can reproduce them in the frequency domains. What does that mean? That means here I might have something, let's just kind of say for the sake of argument, this is a 1 hertz, sorry, this is a 3 hertz signal, a 2 hertz signal, and a 1 hertz signal. If I take the summation of all of those, because I have a linear system, I get this actual response, right? So I'm the one that plotted this. I know that this red line here is just the summation of all 3 of these signals, right? It tends to go up when the red is up. The yellow comes down, it tends to come down because it kind of dominates. It goes back up when the yellow and the green are still high, and then it comes back down to a peak when the yellow and the green kind of match up, and then the blue is just adding some noise on top of that, right? But I have 3 signals. If I were to look at this from this dimension, from that frequency domain, I actually don't see the frequency, right? What I see here is something at 1 hertz, 2 hertz, and 3 hertz. And the height of this line is proportional to the energy that is in that signal, or the amplitude of that signal. You'll notice that the green line is 1 hertz. It also has a very high amplitude. It goes high, low, high, low, high, low. And the orange line kind of has a middle amplitude, and then the blue line has a lower amplitude. So when we look at things in the frequency domain, I no longer have to think explicitly about how they're acting in the time domain, but I can think about how they're acting in this frequency domain. So we will call that a spectrum. A spectrum is that whole field, and you'll have a lot of companies that may work in like telecommunications, like the Spectrum Internet Company. They sell you spectrum, right? And so it's a good name for them. You'll also hear the term bandwidth, right? For the, like broadband internet, high bandwidth communications. That just means like a narrow bandwidth, maybe you just talk over this amount of the spectrum, and a larger bandwidth, you could talk over a broader band of the spectrum. That's where the term broadband comes from. So, but fundamental to talking about things in terms of random inputs.